Hi everyone and welcome back to the first module Windows Internals Overview in the Evasion Lab course by Altered Security. In today's part we will talk about process components, especially threads, token, table of handles, and virtual memory. So let's start by threads. Threads are the units of execution within a process that execute code. They allow a program to execute multiple tasks concurrently. And there is three types of threads: the main thread, threads created by code, and worker threads. The main thread is the primary thread that starts when a program is executed. It runs the main function. Threads created by code are custom threads created by the programmer using functions like create thread. They are used to execute specific tasks concurrently with the main thread. Worker threads are used for background tasks like cleanup, resource management, or input-output operations. They are typically created by thread pools or system services to offload repetitive tasks, improving performance. Threads can be in one of several states, depending on their execution stages. They can be in the waiting state. In this state, the thread is paused and waiting for an event or condition to occur before it can continue execution. For example, a thread might wait for user input or for data to be read from a file. Once the condition is set, Once the condition is met, it transitions to the ready state. In the ready state, the thread is prepared to run but is waiting for a processor to become available. In the running state, the thread is actively executing code on a processor. Threads in Windows operate in two distinct access modes: user mode and kernel mode. These modes define the thread's level of privilege and the type of operations it can perform. In user mode, the thread runs with limited privileges, restricting its access to user mode memory and preventing direct interaction with hardware. It can only access resources allocated to the process it belongs to. The thread uses the user mode stack during this time. In the kernel mode, the thread gains elevated privileges, allowing it to directly access hardware, manage system resources. The thread switch from user mode to kernel mode during system calls or syscalls. When this switch occurs, the thread starts using the kernel mode stack, which resides in protected kernel memory. Each thread has two separate stacks, one for each access mode: user mode stack and kernel mode stack. User mode stack resides in the process user space, which is isolated from other processes for security. It stores local variables, function parameters, and return addresses while the thread executes in user mode. It starts with a small committed space but grows dynamically as needed. And kernel mode stack. The kernel mode stack resides in kernel space, making it inaccessible to user mode applications. Unlike the user mode stack, the kernel mode stack has a fixed size: 12 kilobytes on 32-bit systems and 24 kilobytes on 64-bit systems. And the last thing is the thread call stack. It's a list of functions calls that represent the execution path a thread has taken to reach its current point. It shows which functions were called and in what order, helping developers to trace the flow of execution. Now let's take a look at table of handles. In Windows, the kernel exposes various types of objects for user mode processes, such as files, events, directories, mutexes, and registry keys. However, user mode processes cannot directly access these kernel objects. Instead, they interact with them indirectly through handles, which act as references for pointers to the underlying kernel objects. Every process in Windows maintains its own private handle table, which stores references to the kernel objects it's using. This private handle table isolates each process, ensuring that handles in one process cannot be accessed by another. The handle table keeps track of all the handles a process owns, mapping each handle to the corresponding kernel objects. Each handle in the table has several important attributes. like unique value. Each handle is assigned a unique value within its process handle table. This value acts as an identifier that the process uses to refer to the kernel objects. The second attribute is type. The type of the handle indicates the kind of kernel object it references, such as file, directory, event, mutexes, registry key. The third attribute is the name. Some kernel objects can have a name. And the fourth attribute is the access mask, defines the permissions and access rights the handle grants. This ensures that process can only perform operations they are explicitly allowed to do. Now let's take a look at token. An access token is a security object in Windows that stores the default security context of a process or thread. It defines the identity and privileges of the process, controlling what system resources it can access and what actions it can perform. Every process has an associated access token. The access token stores the user account associated with the process, identifying the logged in user who started the process. It also includes the groups. It also includes the groups the user belongs to, which influences the permissions the process has. For example, if a user is part of the administrators group, their processes will have higher privileges than those of standard user. The access token lists privileges granted to the process, defining what special actions it can perform. For example, only processes with this SE debug privilege can access memory of other processes for debugging or inspection. Now let's take a look at virtual memory. In x64 Windows, virtual memory provides each user process with a 128 terabyte address space, given the illusion of a continuous block of memory. This virtual address space is unique to each process, ensuring isolation and security. The virtual address range for a user process is 0x all zeros to 0x007 all Fs. This large address space allows applications to efficiently manage memory without directly accessing physical memory. Virtual memory is organized into pages, each mapped to physical memory as needed. These pages are arranged in a specific order within the process virtual address space. The first page is user shared data, a read-only page shared across all processes containing system information like current system time, tick count, time zone settings. The second pages are the PEP, the process environment block. Stores information about the running process, including its image base address, loaded modules list, process heap, and stack addresses. The third pages are stacks. Each thread within the process has its own user mode stack that store local variables, function parameters, return addresses. The fourth order pages are the heaps. Dynamic memory allocation is managed through heaps, allowing the process to request and release memory during runtime. The default process heap is created by the system, but applications can create additional private heaps for better memory management. The fifth memory pages are NLS and MUI files. The sixth memory pages are allocated pages. They are dynamically allocated memory pages used for various tasks. They are managed using API like virtualalloc and virtualfree. The seventh order of pages are executable file image. This section contains the image of the executable file that started the process mapped into memory. And the eight order pages are modules. Dynamically loaded libraries LLs required by the process are mapped here. This includes both system libraries like kernel32 and ntdll.dll and custom DLLs loaded by the applications. Virtual memory pages in Windows can exist in one of three states: pre, committed, or reserved. These states indicate whether the pages are allocated or simply reserved for future use. Free. Pages in the free state are not allocated and are available for future use. Committed. Are allocated and mapped to physical memory or page file space. Reserved. Have a reserved address space but no physical memory is allocated yet. Their pages are set aside for future use. Virtual memory pages are also classified by their type, which determines how they are used and managed by the system. Mapped pages are associated with files on disk. They allow a process to access file data directly in memory. Private pages are exclusive to a process and cannot be shared with other processes. Image pages come from executable files .exe or .dll loaded into the process address space. Each virtual memory page has a protection attribute that determines the allowed operations. The main protection types are read. The page can be read but not modified. RW, read write. The page can be read and written to. X, execute. The page can only be executed as code. RX, read execute. The page can be read and executed but not modified. RWX, read write execute. Full access. The page can be read, written to, and executed. No access. The page is inaccessible, preventing any read, write, or execute operation. Guard, used to detect buffer overflows or stack expansion. Accessing a guard page triggers an exception, allowing the application to handle it safely. Now let's take a look at some properties of these process components using Process Hacker and start by threads. So let's launch a CMD process and inspecting its threads, and we can see there is two threads, the main thread and the worker thread. In the worker thread, it's used for cleanup, resource management, memory management, and this is the CMD main, which do the entire CMD operations. And we can see in this is the call stack, the thread call stack, which is a list of function calls that represent the execution path a thread has taken to reach its current point. And we can see in this current call stack, we can see two distinct access mode, which is the user mode, finish as at this ZW device IO control file, which contains the system calls that switch the execution flow from user mode to kernel mode. In this user mode access, only the user mode stack is used, and in this kernel mode access, the kernel stack is used. And we can see here in user mode, the loaded modules and the executable file image is used, like the main of the executable file image function, the main function, and here some function exported by some DLLs. And the user mode and the kernel mode access mode, we have some exported functions executed by the kernel here is executed. And the last function executed here is the key check for kernel EPC delivery, and the first function executed by this thread is RTL user thread start. This is like the lifetime of the thread, starting from a point and finishing at a point. And this thread is actually, we can see that the working thread is killed. We have only the main thread remaining, and here this main thread is in wait state, waiting for an event or condition to occur before it can continue execution and do the transition to the ready state. Now let's take a look at some table of handles properties. And every process here let's open this other process running with high integrity, and this is the process CMD process running with medium integrity, and we can see that each process maintains its own private handle table, and each handle in the table has several important attributes like unique value, which is this value is uniquely identified and it's different than other handle. And we have the type, which is the type of the handle indicates the kind of kernel object it references, such as file, directory, registry key, mutant, thread. And here we have each handle has a name and the access mask, which represents the permissions and access rights the handle grants. Now let's take a look at the token. And we can see the access token stores the user account associated with the process. And we can see that the user account is student user1 in this case. And the groups the user belongs to, which belong to the built-in users and other users. And as this process is running with medium integrity, you can see only 2 privileges granted to the process: the SE change notify privilege and SE increase working set privilege. And we cannot use those privilege only if we enable them. And if we open this higher integrity CMD process and take a look at its token, we can see a lot of token that the other CMD process with medium integrity doesn't have. And part of these tokens, the privileges we have is SE debug privilege that allow the process to debug other processes and run and read its memory or inject something to its memory. And if we enable this SE debug privilege, we can debug other programs. Now let's take a look at the memory, and we can see it's starting from a lower memory range, nearly to 0000, and it finished at 0FFFFFFF. This is the last mapped loaded memory, which is intdll.dll, and we have this file image loaded at this memory address. And the pages have a typical order. We have user shared data that comes first, then the pub, then the stack, then the heap, then the NLS and MUI files, then the file image allocated memory, pages, then the file image, then the loaded modules. And we have 3 states for each virtual memory pages, either in committed, reserved, or free. Here it's committed page, here it's committed or reserved page. We can find a free page maybe. And we have also the type of the page, either private or mapped or image in this case. And we have also the protection of each page, either read write, or here rx, which is the .txt section of the file image in this case.